Hello and welcome to this latest in the series on Vine copulas. Now, last time we looked at conditional densities and conditional copulas, but we looked at it in a two-dimensional setting. And that's because when you're trying to work out how these things work, you do it in the most straightforward, the most basic approach possible, and that's with two variables. But two variables isn't a Vine copula. You've got to have at least three variables to have a Vine copula. So what we're going to look at now is some of these conditional expressions moved into three dimensions, because that will then allow us to use these with Vine copulas. So we're going to look at densities for three-dimensional Vine copulas, and we're going to start by looking at the likelihood function, because if you're using maximum likelihood estimation, then you need to maximize the likelihood function. Even if you're not doing maximum likelihood estimation, it's still useful to find the likelihood function, because when you've parameterized some data some other way, if you work out the likelihood function, that allows you to find out how good your fit is using one of a range of tests. But anyway, so your likelihood function for three dimensions is the product from t equals 1 to t of f of x1t, x2t, x3t, and t is each observation, so from 1 up to how many observations you've got. So if you've got, say, I don't know, 3 years monthly data, then it's going to be 36 observations. So what this means is, in terms of the function that we're interested in, is essentially f of x1, x2, x3, because we're not usually going to be able to evaluate this straight off, but we are going to have more of a chance if we can break it down into its component parts. And those component parts are univariate marginal density functions and some tractable, workable copular density functions. So, if you think back to last time's video, we know that f of x1, x2 is equal to f of x1 given x2 times x2. So we can move that to three dimensions, and we can say that f of x1, x2, x3 is equal to f of x1 given x2 and x3 multiplied by x2, f of x2, x3. And we can then use that same expression on that final term, f of x2, x3, to expand it further and say f of x1, x2, x3 is equal to f of x1 given x2 and x3 times f of x2 given x3 times f of x3. Now, that's already helpful. It's broken it down considerably, and we've already got one marginal density function out there, but we can also decompose this further to include copular density functions. So let's start with that previous expression. f of x1, x2, x3 is f of x1 given x2, x3 times f of x2 given x3 times f of x3. We know that f of x1 given x2 is also equal to c of u1, u2 times f of x1. So it's the copular density on the distribution functions u1 and u2 times the density function for x1. So if we use this on these individual terms, we can also say that f of x1 given x2, x3 is equal to c of u1 given 3, u2 given 3 times f of x1 given x3. So what we've essentially, and that's equal to c of u1 given 3, u2 given 3 times c of u1 given 3, f of x1. So again, just breaking down that final term. We can also say that f of x2 given x3, the second term in that first line, is equal to c of u2 and u3 times f of x2. And if we combine this with that final term on the top line, f of x3, we can get f of x1, x2, x3 is equal to f of x1 times f of x2 times f of x3 times c of u1, u3 times c of u2, u3 times c of u1 given 3, u2 given 3. So we've managed to break it down to something which looks a lot more tractable, essentially marginal distribution functions and some copular density functions. And there is a sort of graphical way of looking at this. If you think about a Vine copula, which has 3 in the middle and a 1 and 2 either side. So this is the copula we're kind of working with. So our variables are 1, 3 and 2 in that order, and the copulas joining them are 1 and 3 and 2 and 3. It's the copula joining 1 to 3 and the copula joining 2 to 3. So that's the first line of that diagram, the blue blocks. Now, what you can also do is say, well, let's take those two copulas, the copula between 1 and 3 and the copula between 2 and 3. What is the copula that joins those copulas? Well, we can see that in those grey blocks, we've got a 3 in each. So essentially the copula that's joining those grey blocks is the copula between 1 and 2 given 3, because 3 is common to both of them. Now if we look over to the left-hand side, we can see how this reflects that expression. The first line is f of x1, f of x2, f of x3. So that's the marginal density functions for those three variables. Then you've got the copular density functions, c of u1, u3, c of u2, u3. That's the copulas joining those variables. And then in the bottom, you've got c of u1 given 3, c of u2 given 3. And that's essentially the copula joining the copulas. Now, this is the unique decomposition for this particular copula, but it's not the only way that you can decompose f of x1, x2, x3. In fact, there's 6 possible decompositions. I'm not going to go through them all. You can pause the video and work it out for yourself if you like, but there are essentially 6 versions of that equation that I worked out, and each of them will be appropriate for a different Vine copula. So there are more ways of doing it than I've just shown, but if you want one which represents what I just showed, then that expression is it. So as I say, the structure shown is given only by this expression here. So f of x3 in the middle, f of x1 and f of x2 on the sides is given by f of x1, f of x2, f of x3 times c of u1, u3, c of u2, u3 times c of u1 given 3, u2 given 3. So f of x1, f of x2, f of x3, those are all straightforward. They're just marginal density functions, which is how probability functions are usually given. C of u1, u3, c of u2, u3 is perhaps a little bit more difficult, but not necessarily so. So if you're looking at an elliptical copula, then they're essentially defined in terms of density functions anyway, so they're not too bad. Archimedean copulas, you can differentiate them, as we've shown. So you can differentiate the copular distribution function to get those copular density functions. The last one, a little bit more tricky. That's where the challenge really lies. And there's a couple of challenges here. The first one is that when we're setting up our Vine copula, we're not actually explicitly defining the copula between f of x1 and f of x2 in this case, but we need to decide something. We need to come up with a structure for that, for this conditional copula. And we also need to come up with u of 1 given 3 and u of 2 given 3. Now, there is I won't say a cheat, but there is a way around this. One solution is, if you assume that x1 and x2 are independent given x3, that implies an independence copula. And if you remember back probably a couple of videos, what this implies in terms of the copular density function is that the copular density function is 1. So the joint density simplifies to f of x1, f of x2, f of x3 times c of u1, u3, c of u2, u3. And if this assumption is made for all conditional copulas, then life gets very much easier. And we only need to worry about the specified copulas. But if you're going to do this, you need to be confident it's realistic. And if it's not realistic, then you have to do things the hard way. If x1 and x2 aren't independent given x3, then you need to pick a copula. And you can assess the fit as part of the MLE process or by eyeballing the data to see whether it fits the observations that you have. But you do still need to find those observations. And those observations are u1 given 3 and u2 given 3. Now, the way that we get these is by partially differentiating the copulas that we already have between 1 and 3 and between 2 and 3, which we're already selecting. So if you remember, u of 1 given 3 is equal to capital F of x1 given x3. And to find this, we essentially take the copula distribution function for f of x1 and f of x3, or u1 and u3, and we partially differentiate it by f of x3. So essentially, the partial differential of c u1 u3 by u3. And similarly, u2 given 3 is the partial differential of c u2 u3 by u3. So it is not necessarily straightforward, but it is possible to find these variables and plug them into the copula that we choose. Now, this function is actually known as an h function, the partial differential of the copula with respect to one of the uniform distributions is the h function, h of u1, u3. And in this, the first term is, in the expression, is conditioned on the second. Now, these are quite useful functions, quite useful shorthand, and it gets used in likelihood functions and also in simulation. So we will see this reappearing from time to time. And this is what some h functions look like, which I have not worked out myself. I've taken from papers that others have written on this subject. And you can see they're reasonably, most of them are reasonably tractable. I mean, the gumball one isn't the nicest because part of it is already a copula distribution function, so you need to take that into account. And again, for the elliptical functions, bivariate ones, which are the ones we'll be using, again, it's relatively straightforward. Even more straightforward if someone else has actually worked it out for you, but this is what the numbers look like. So there we go, that's something on three-dimensional work in terms of conditional copulas, and that gives us the building blocks that we need to be able to fit data to three-dimensional Vine copulas, which is what we're going to be doing next time.